Morning students. So today the topic of discussion will be Unit 5 Pulse Modulation. So far in the previous classes we might have learned about what is sampling theorem for low pass signals, what is quantization, and of course we also discussed about the various effects of quantization, noise, and few compounding techniques. So with the knowledge of sampling and quantization, we now move on to our next topic of discussion where we try to focus on pulse modulation. So now let us quickly recollect our course outcome 5 for 5th unit. So here we try to verify sampling and quantization technique with the help of which we also try to implement pulse modulation methods. So what is pulse modulation? So pulse modulation is actually it includes both analog as well as digital. In the previous units where we discussed about amplitude modulation, frequency modulation and phase modulation, those methodologies were coming under continuous wave type. Whereas in case of pulse modulation, our input signal will be of analog type, which is a continuous waveform. So this is your input signal or the modulating signal, and your carrier signal will be of a pulse train. So this is a carrier pulse train. So as we all know already, this pulse modulation is further divided into pulse amplitude modulation, pulse width modulation, pulse position modulation, and also pulse code modulation. So in the previous class, we have already seen the basic concepts of how a pulse amplitude modulated signal is being generated, and we also discussed about the method of generation of PAM signal as well as the demodulation of PAM signal. We of course discussed about the advantages, disadvantages, and few applications where we try to deploy pulse amplitude modulation methods. So now let me quickly rush through the concepts of PAM and then slowly we will move on to the concepts of PWM and PPM in today's class. Yes, so what is pulse amplitude modulation? So in pulse amplitude modulation, we try to vary the amplitude of the original signal, which is your carrier pulse signal here, according to the amplitude of the modulating signal. So this is the modulating signal and this is your carrier pulse signal. So we try to vary the amplitude of our carrier pulse according to the amplitude of the modulating signal. So our modulated waveform will be like proportional to the instantaneous amplitude of this message signal component. So under pulse amplitude modulation, we have once again two categories. One is flat top sampling and the other one is natural way of sampling. So we also went through the waveforms. So this waveform represents natural PAM, natural pulse amplitude modulation, and this one represents flat top where the pulses retain flat tops, right? So compared to the previous, which is your natural PEM, flat top sampling method is preferred in almost all transmission techniques. Here we can reduce the interference of noises and comparatively the distortion is less. So next we'll try to move on with our today's topic of discussion, which is about pulse width modulation. So what is pulse width modulation? So here the parameter which we are going to vary is about the width. So in case of pulse width modulation, we try to vary the width of the pulse according to the amplitude of your modulating signal. So the carrier pulse width will be proportional to the instantaneous amplitude of the message signal. So let me just show you the waveform. So this is the carrier pulse and this is our input signal or the modulating signal. And you can observe three different waveforms. The first waveform, so this is one kind of pulse width modulation. So where, just observe, we try to fix the leading edge of the pulse as constant and we try to vary the trailing edge of the pulse. And in case of the second waveform, just observe, the trailing edge. So this is the trailing edge. The trailing edge of the pulse is maintained constant with respect to the carrier pulse. So carrier pulse is our reference. So we try to fix the trailing edge of the carrier pulse as constant, and we try to vary the leading edge of the pulse according to the amplitude of the modulating signal. And finally, the last waveform here, the center of the pulse is maintained as constant with respect to the carrier pulse, and both the leading edge as well as the trailing edge is being varied according to the instantaneous amplitude of the message signal or the modulating signal. Yes. So this waveform is representing pulse position modulation. So here previously we have discussed about pulse width modulation. So where we try to vary the width of the pulse according to the amplitude of the message signal, and in case of pulse position modulation, we maintain both the width and amplitude of the carrier pulse as constant. So this is the carrier pulse, this yellow color waveform. Okay, and we try to just vary the position of the carrier pulse according to the amplitude of the message signal. So here actually we, as a first step, we try to generate pulse width modulated signal, and we keep this PWM signal as a reference, and we in turn generate PPM signal. PPM means pulse position modulation. So here I try to vary the position with respect to the trailing edge of my pulse width modulation. Okay, so I just shift the position of my pulses here, whereas this PWM is kept as constant. So this kind of modulation is known as pulse position modulation. Yes, so here we have a comparative chart where we try to analyze pulse amplitude modulation, compare the waveform with pulse width modulation. Once again, pulse position modulation. So this graphical representation has a comparison, waveform comparison between all these three modulation techniques. So you can very well observe here, right? So in case of the first one, PAM output, I try to vary the amplitude of my carrier pulse. So this is my carrier pulse. I try to vary the amplitude of the carrier pulse according to the message signal. So this is your PAM output. And next comes PWM, pulse width modulation, where I try to vary the width of my carrier pulse. See, I try to vary the width according to the amplitude. So this is the amplitude of the modulating signal. So as it is going to the peak point, I try to vary the width of my pulse here, right? So this is known as pulse width modulation. So the width is modulated. And the last one, which is pulse position modulation, here I just try to vary the position wherein I keep width as well as the amplitude of the carrier pulses constant. So the width as well as the amplitude of the carrier is kept constant, but I try to vary the position of the pulses keeping PWM as the reference. Okay. So with this discussion, we'll wind up today's session, and in the next class, we'll move on to the next type of pulse modulation techniques, which is actually coming under digital modulation, which is known as pulse code modulation. Thank you.